Howdy, folks. I reckon this will be my last video on basic mathematics. Let's see how far we got up to this point. We've covered essentially 7 different topics: BB6, the order of operations, column arithmetic, a bit on long division, and quadratic equations, and more generally, polynomial equations. Now, if you remember, at the end of the last video, I mentioned there were certain polynomial equations that it's just not possible to solve exactly. Our friend Everest Galois showed us this. So that means sometimes you need to use a computer or a calculator to solve equations in general. Today's video is all about good calculator hygiene. Now remember, whilst a calculator is a wonderful thing, a calculator cannot do everything. You need to know how to use your calculator, and also that what you're inputting into your calculator actually makes sense. If you've watched the TV series, The Hitchhiker's Guide to the Galaxy, one of the many jokes in this series is a race of aliens want to know the answer to the question of life, the universe, and everything. So they built this amazing computer called Deep Thought, and it took thousands and thousands and thousands of years to build this thing precisely to answer this question. So finally, Deep Thought has mulled over this for forever, essentially, and he comes up with the following answer. So the answer to the great question of life, the universe, and everything is, so there's 2 philosophers who are waiting for this answer, and he says, well, you're not going to like this answer. But anyway, he tells them eventually the answer is 42. And the reason why I guess this is funny is the question itself doesn't really make any sense. If you don't know what you're asking your calculator to do or your computer to do, you've got a snowball's chance in hell of ever getting out the correct answer. Because if the question isn't correctly formulated and inputted correctly, you're all at sea. So what I thought I'd do is list for you 4 or 5 common pitfalls that people make when they're using their calculators to solve problems. It's not an exhaustive list, but it's a good starting point. Let me begin with an example. Let's try and do the following calculation on our calculators. So let me have a think. On your calculator, compute the following. Let's work out sine 30 degrees, cos of 30 degrees, and tan of 30 degrees. So what I do is I nip onto the internet. I'm using a program called Desmos, which is good at, well, it basically mimics a calculator amongst other things. Let's work out, to start off with, sine 30 degrees. So sine 30 degrees equals minus 0.988 something or other, something or other, something or other. Let's do cos 30 degrees next. 0.15425, blah, blah, blah. And finally, tan of 30 degrees. Tan of 30 degrees gives me minus 6.40533, and that's indeed sine 30 degrees divided by cos 30 degrees. That all seems reasonable. Sine and cosine are taking values between -1 and +1, so everything is rosy in the garden, right? No way. In fact, I know what sine 30, cos 30, and tan 30 are exactly because I have this right angle triangle here. So the side lengths of my triangle are 1, square root of 3, and 2. Sine 30 degrees is opposite over adjacent, so sine 30 must be a half. Cos 30 is adjacent over hypotenuse, so that's root 3 over 2. And finally, tan 30 is opposite over adjacent. That's 1 divided by root 3. So in this situation, I actually know the true values. Let me put them in for you. The true values are a half, root 3 over 2, and 1 over root 3. In other words, sine 30 divided by cos 30. So that's 0.5. That's, I don't know, 0.866 something or other. And this last one is 0.5774, etc. Well, how does that compare to what we've just worked out on the calculator? Let's have a look. What did we work out on the calculator? We worked out the following values: minus 0.988 plus 0.154 minus 6.4. Anyone know what went wrong here? Well, in a sense, the numbers I put into the calculator were absolutely fine, but I didn't check whether the calculator was using degrees or radians. If it's not set up properly at the start, you're going to get the wrong answers. So here, if you note down here, it's radians rather than degrees. If I switch it to degrees, suddenly I get the correct values: a half, root 3 over 2, and 1 over root 3. So there's a lesson there for us already. Make sure when you're using your calculator to see whether you're in the degrees setting or the radian setting. That's very important. That's one potential banana skin you can come across. Let's look at another one. So my second word of warning to you is the following. I'll do a different example with you. So let's move on from this one and instead evaluate a particular expression that I introduced in my very first video. So again, on your calculator, evaluate the following. Evaluate 12 cubed divided by 4 plus 5 times 6 plus 7 times 8 plus 9. Let's give it a go then. This is lifted directly from one of the examples in my very first video. So I nip onto my calculator and I start inputting numbers. 12 to the power 3 divided by 4 plus 5 times 6 plus 7 times 8 plus 9. What do I get? I get 17.454545. In other words, 17.45 recurring. Seems reasonable. I've no reason to doubt this value. Have I done everything correctly? Let's go back to our original expression. Our original expression over here was this thing. And I know from later on in my first video, we actually worked this out. We found out that the answer was 1,057. Does 1,057 agree with what I've put into my calculator? It doesn't appear to be at all. It's very far away from it. Okay then, what have I done wrong here? Here in my original expression, I had a whole bunch of brackets. And when I inputted the values into my calculator, I completely ignored the brackets. That's a big no-no. If you don't put the brackets in, you're going to change the expression that you're evaluating. So your calculator can cope with BADMAS, providing you parenthesize things correctly. So our second conclusion is, when you're inputting information into your calculator, make sure you've put in the right expression. There's nothing worse than having the correct expression on paper, and then when you transfer it to your calculator, you stuff up at some point. All right then, moving on, let's look at another example where we could potentially slip up. So the example I want to look at now, if we've finished with this now, let's again do a calculator calculation. Let's calculate the following. So we're going to work out inverse sine, so arc sine of 30 degrees. Same for cos, inverse cos of 30 degrees. And finally, inverse tan of 30 degrees. Now, just remember, when you take the inverse function undoes what the original function does. So sort of in my soul already, I know what the answer should be. In each case, surely the answer should be 30 degrees. So I'm expecting the following values. I'm expecting, 30 degrees, 30 degrees, and 30 degrees. Let's see how we do when we plug it all in. Check that I'm using degrees, because that's where I slipped up before. I'm using degrees correctly. It's been set into my calculator now. So now I go to the inverse function so I can get more functions. I want to take inverse sine of 30 degrees and see what I get. I get 30 degrees back. Excellent. Let's do inverse cos of 30 degrees. I get 30 degrees again. Everything's wonderful. Lucky last, inverse tan of 30 degrees. I get 30 degrees. Clearly, there's nothing wrong with using inverse sine, inverse cos, and inverse tan on my calculator. Well, let's just see a moment. I'm going to do 3 more of these for you. So rather than take 30 degrees, I'm going to take 130 degrees, say. So I want to compute now inverse sine of 130 degrees, inverse cos of 130 degrees, and last of all, inverse tan of 130 degrees. And I want to see what I get. So I nip onto my calculator app. Let's do the same procedure again. So inverse sine of 130 degrees. I should get 130. What? I get 50 degrees back. Maybe that's just an aberration. Let's do inverse cos of 130 degrees. Oh, that's reassuring. I get 130 degrees back. Everything's great again. Last of all, inverse tan of 130 degrees. What? I get minus 50? What on earth is going wrong? My calculator must be defective. It's producing me these crazy numbers. How can that possibly be? Well, in a sense, the calculator isn't doing anything wrong at all. The calculator's doing its best. We just haven't thought things through enough. Let's go back to our definitions here. In blue, I have a sine wave, and in red, I have a cosine wave. So initially, I worked out sine of 30 degrees. So 30 degrees is about here. Sine of 30 degrees, I go up, and the value I get, I've worked this out before, this is about a half. So I'm out here. Then I take inverse sine of a half. I go splat back onto my blue wave, and I get 30 degrees back. No troubles at all. Same thing with cosine 30 degrees. Cosine 30 degrees, I go up here. That bounces off to give me about y equals root 3 over 2 here. And then I bounce back and I return 30 degrees again. Let's move on to what I did when it was 130 degrees. So 130 degrees is about out here, say, approximately. So starting with the sine wave, 130 degrees, I bounce up here. I get a y value out here. And then I bounce back, but I don't hit the blue part of the wave as it descends. I hit the blue part of the wave as it increases. So when I hit the blue part of the wave, I get about, I think it was 50 degrees out. Let me just check for you. What values did we get? We got plus 50 degrees. The correct value for the cosine, inverse cosine of cos, and then the wrong value for tan again. So what's going wrong here is the following. When I'm over here with 130 degrees out here, I bounce up, bounce onto my y-axis, but when I bounce back, I collide first with the increasing sine wave rather than the decreasing sine wave. So that throws off my value. With cosine, there's no problem. If I have cosine 130 degrees, I go down here, bounce onto here, and then I take inverse cosine, I bounce back to get 130 degrees again. The problem is precisely this. The domains of definition of inverse sine, inverse cos, and inverse tan are all slightly mixed up. So inverse sine takes values between minus 180 and, minus 90 and plus 90 degrees. Here it's written in radians, but if you convert this into degrees, that's minus 90 degrees and plus 90 degrees. For inverse cos, it's between 0 and 180 degrees. Last of all, inverse tan behaves like inverse sine. So it gives you values between minus 90 degrees and plus 90 degrees. That's why my values that I computed over here, they were thrown out when I computed inverse sine and inverse tan, but they were correct for inverse cos. So inverse cos agreed, but the other two were not what I expected. This one was 50 degrees and this one was minus 50 degrees. All I'm saying here is be super careful when you just blithely take inverse sine, inverse cos, and inverse tan on your calculator. You need to make sure that the ranges of the three functions coincide with the ranges that your angles are corresponding to. So our moral message from all this is understand how the different ranges of these trig functions behave when you take their inverses. That's very, very important. People often think the calculator has got inside your head and knows exactly what you're thinking, but you have to be careful because the calculator doesn't know anything about you. You have to tell it precisely what you want it to do, and then the answer that it returns should be more or less correct. Okay, second last example I want to look at is the following. Suppose we compute the following inverse functions again. So remember, the exponential function is something that you'll be introduced to probably at NCEA level 2. If I compute the exponential function raised, or rather e raised to the power log of 100, I expect for the answer 100. Likewise, if I take 10 and I raise it to the power of log of 100, log of 100 to the base 10 is equal to 2, so that should be 10 squared, which is 100 back at you. So I know both these facts are actually true. My calculator surely should verify both these identities here. Let's have a look. I feel like I'm picking on the calculator today, but let's give it a go. Let's start with e to the log of 100. So e to the power x, that gives me e to the, where's my log gone? It's probably over here somewhere, log of 100. What do we get? Well, according to our calculator, we get 7.389, blah, 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 blah. That doesn't seem to agree with what I actually know to be true, is that e to the log of 100 is 100. Okay, well, let's do the second one. Maybe my calculator's having a bad day, who knows? Suppose I work out 10 to the power log of 100. What do I get? What? I get 40,287 point blah-de-blah-de-blah. That's not agreeing with what I know is true over here. What on earth am I doing wrong here? I'm misusing my calculator. I'm being sloppy. You'll notice here in the first expression, I took log to the base 10 rather than the natural logarithm. In the second expression, I took log to the base e rather than log to the base 10. So of course, these two values are thrown off. If I want to get the correct values back, I need to replace this first one by the natural logarithm. And then the second one, I need to take log to the base 10. And then in both cases, I'm getting 100 and 100. So what can we glean from yet another mistake Daniel's made? We can glean the following message. When you're taking the logarithm, be sure to choose the correct base. It's easy if you're working at speed to miss which base your logarithm is to. If it's written as log, the convention is it's log to the base 10, unless you specify otherwise. If it's ln, it's log to the base e. This may be something that you encounter sort of in your final 2 years of school, but earlier on, you don't meet the logarithm function at all. It's only later on. All right, then. Lucky last warning to you is the following. So I want to talk about a common phenomenon that people often forget about. To illustrate with an example, let's just say, how should I phrase this? It's a well-known fact, it is well known that if you compute the following function f of n, which I'll call 1 plus 1 over n to the power n, then if n is very, very big, this is approximately equal to the number 2.71828, blah, blah, blah. And this is only true, this approximation, if n itself is very large. Going back to my previous example, if you know a little bit about NCEA level 2 and level 3 maths, this number is the number e. It's one of those fundamental numbers that turn up in mathematics. Well, this is absolutely true, this fact, providing n is ginormous. So as an exercise, let's compute f of n for various values of n. So let's compute f of n for, I don't know, n equals 10 to the 1, 10 squared. Let's increase the number 10 to the 10, and maybe lucky last, 10 to the 100. So here I'm increasing n with each successive choice here. So on my calculator, I need to compute f of 10 to the 1, f of 10 squared, f of 10 to the power 10, and lastly, f of 10 to the power 100. 10 to the power 100, at least in my book, is a large number. So let's flip over to our calculator again and see what we get. Let's start with 10 to the 1. So I take 1 plus 10 to the power 1. Whoops. All raised to the power 10 to the 1, I guess. So that should be 10 to the minus 1 if it's truly 10 to the 1. Let's see what we get. We get about 2.5937. Let me put this into my list here. So I've worked out the first one of these. This is equal to 2.5937. It's kind of close to E, but it's still quite a bit of a way off being equal to E. Let's shift to 10 squared. See what we get. If it's 10 squared, it's 2.7048. Let's pop that in. 2.7048 rather. Okay, so we're getting closer and closer and closer. Let's try the third one. So now we're looking at 10 to the 10 here. What do I get? Oh, I'm really close now. 2.71828. I'm almost there, I reckon. So I've got 2.7183 blah, blah, blah. I reckon when I put in 10 to the 100, I should be absolutely smoking it. So here, if I put in 100 here rather than 10, I must really be there, right? A equals 1? How can that be? That's outrageous. How can that be equal to 1? I was doing so well. As I was going down, I was approaching the true value of E. And suddenly, my calculator's thrown a wobbly, and when I've put in n equals 10 to the 100, which is a huge number, my calculator has let me down completely. There's no ways that this coincides with the number E. So what's gone wrong here? This is a little bit subtle. Your calculator only has a finite amount of memory. So if you take 1 plus 10 to the minus 100, it stores that as a floating point number, but it can only store so much of it. So the part corresponding to 10 to the minus 100, it's got lost off the end of the display, or rather the storage of that number in the calculator. So once you put in 10 to the minus 100 and you add it to 1, the calculator goes, I can't cope with this. I can only do floating point arithmetic. I can't see the 10 to the minus 100. It only sees the value 1 at that point. So when you then raise 1 to the power 10 to the 100, you still get 1 back. Your calculator has limitations. It's limited by its memory. And quite often when you're doing, reasonably complicated calculations, you get these sort of numerical instabilities coming in. So yeah, we should be proud of our calculator, but our calculator can only do so much to help us. So don't allow rounding errors to creep in. And this is a nice little example where that occurs. Think of it this way. If you're a speed skater, providing you have good technique, you should do very well in your race. But just occasionally, things can go awry. If your numbers are a little bit off, then everything comes unstuck. That's called doing a Bradbury, by the way. So treat your calculator with respect, but also understand its limitations. When I'm doing a test or an exam, or when I used to do them, I try and do as much of the calculation by hand as I possibly could. And in fact, if I could do the whole calculation by hand, I'd be really happy. And then at the end, I just check on my calculator that it actually made sense. That is pretty much it for my basic maths videos. I've got heaps more videos to come, but thank you very much for listening to me.